This is a little bit on the background in trigonometry. We've done some calculations with it now. You've got the basic ideas. We now need to see how does it work and why does it link together to a certain extent. So the initial point was start with two regular shapes. We've got a square, side of 1, an equilateral triangle, side of 2, and you're asked to separate them into identical triangles, pairs of identical triangles. So when you put the diagonal through the square, you get two triangles, one with a right angle, a 45 degree, two sides of 1 centimetre, and this hypotenuse. When you do the same thing with the equilateral triangle, you've got 60 degree in the corner, a right angle on the side, and this 60 at the top is split, so you've got 30 degrees with a side of 2. So when we come to actually playing with these, let's go down and work through on each triangle. So the first standard triangle has two sides of 1 and a 45 degree. Using Pythagoras' theorem, we know that the hypotenuse is equal to the sum of the squares on the square. The height square of the hypotenuse is equal to the sums of the squares of the other two sides. So 1 squared plus 1 squared is 2, square rooted to give us our hypotenuse 2. Now we've got sides and we know the angles are 45, we can do SOHCAHTOA. So sine of 45 is opposite over hypotenuse, 1 over square root of 2. And this is a little side note, square root of 2 on the denominator is often frowned upon, but they're easy enough to remove by multiplying top and bottom by the same thing, the same square root. So if you've got a square root on the bottom, if you multiply by square root 2 on top and bottom, we won't change the values. Square root of 2 times the square root of 2 is going to be a value 2, so we've got the square root of 2 over 2. That's our sine value. Cosine is a 1 over square root of 2, but this time it's this 1 for the adjacent divided by the square root of 2. And again gives us the same answer, square root of 2 over 2. Tangent of 45, opposite over adjacent, gives me a value of 1. And a little side note for you about tan, and one of our first meanings, is the tangent of an angle is the line that's going through that angle sloping upwards. And when we see sloping lines, we often ask, what's the gradient? Well, gradient is the change in y divided by the change in x, or the rise over the run. So the rise over the run is the opposite over the adjacent. So tan of 45 is also the gradient of the line. So that's all the 45 degree triangle. And we've got some magic numbers for it. Magic numbers for the 30, 60, 90 triangle. Well, we've got a hypotenuse, which is the sloping side of the triangle, is 2. Half the base is 1. So we can use Pythagoras again to work out what the missing side is. So hypotenuse squared is 4, is equal to our unknown side squared plus 1 squared. So that gives us this unknown side is the square root of 3. Again, do SOHCAHTOA for each part. So the purple labelling is so we can do sine of 60, opposite over the hypotenuse, so square root of 3 over 2. Cosine of 60 is the adjacent, the 1 over 2, a half. And tan of 60 is the square root of 3 over 1, or square root of 3. But we've got another angle, the 60 at the top here, and we relabel it for opposite, hypotenuse and adjacent again. The sine now is 1 over 2, opposite over hypotenuse. Cosine is the root 3 over 2, the adjacent over the hypotenuse. And the tan of 30 is the 1 over the square root of 3. That 1 over the square root of 3, again we need to do the little trick for surds, multiply the denominator by the same surd and multiply the top by that surd, and it will get rid of this denominator with a square root. So root 3 over 3. Magic numbers. Now, there's a number of bits and pieces in here. I've been asked where the words sine and cosine come from. Well, going back into ancient time, I think it was a Greek called Hippocarius was investigating the angle at the centre of a circle compared to the length of the chord, and he made some assertions. About 1,000 years later, the Persians and the Indians started investigating half the chord and the angle at the centre, or the half angle at the centre. And they started making lists of tables of values. And those tables of values, I think they would called it something to do with whole, a part of the whole circle. And so they called it their equivalent of a whole. That got translated back into Greek or Latin for us. So that whole became a word sine or sinus, meaning hole in the head type sinus. Shortened to sine, and the other side, the cosine, cosine, just means something that varies with it. So that's where the naming came from. So let's have a look at these triangles then. I'll bring up the sheet. This one's not been made by me, this isn't mine. A guy called Ben Sparks. You may know him from doing watching things like Numberphile on YouTube. He works quite a lot with a guy called Matt Parker as well for maths related things. So we've got a point on a circle moving round, and this is an alternative. We've just dealt with the sine and cosine as a ratio. But if I actually pause this, we've got a radius of a circle with an angle at the base. If I put in sine, we suddenly see a right angle triangle. And this side, if it's 1, there's the angle at the centre. The opposite side is this side. So opposite over hypotenuse is sine. If the radius is 1, the height on this unit circle must be sine of theta. And that will actually move round on this circle. As the angle steadily increases, the height increases quickly to start with and then slows up. Starts going negative quickly, goes quickly and then slows up towards the negative 1, and then comes back up. And that creates this, what's called the sine curve. If I then look at another triangle, I would prefer to say this red line should be going across the bottom of our original sine triangle. So this line, red line here, is the same as the line between the end of the blue and the angle. But there's another right angle. Compared to our angle, if I stop it, this side here is adjacent to my angle. The hypotenuse is 1, so the red line is the same as a red line here. So we now have cosine is the x-coordinate of this point that's moving in a circle. And they keep moving round to give us x and y points. So cosine is the x-coordinate, sine is the y-coordinate. And if we put in tan, tan is the slope of the line. So if we do the gradient of this line, that gives us our gradient m. If we set x to being 1, the height of this line, where it is above that 1, is the tangent. So that's how those three formulae all come together, and it creates this formula, these graphs. Now I've asked you to create the graphs yourselves, putting the numbers in. It's a reasonable exercise to do because it helps you understand which bits are doing what, and it also helps you look for symmetries. When you start doing these for even numbers around 90 and these even spacings, what you'll find is your numbers pair off around the 90. In terms of the cosine, they pair off around the 180 or coming back from 360. So the exercise is partly to find out where the patterns repeat and what the repetitions are for, because that helps us solve further problems using sine and cosine. The last thing I'd like to mention is if we actually stop the animation again, there is actually a quick relationship with Pythagoras. We've got a side of a right angle triangle, a side of a right angle triangle, and the hypotenuse. So if we square the height, sine squared, square the adjacent side, cos squared, those two sides added together is the same as the square of the hypotenuse, which is a 1, because we've got a circle radius 1. So sine squared plus cos squared should always be 1. And that's the result.